We're going to do notes too, so that'll help. So right here, we picked 1, and we got this green line. At 1/2, even closer, we got this line. Now, we didn't do this, but what about if I used like 1/10? I could do, I'm going to do this, I'm going to do the slope formula right here. So if I use 1/10, 1/10, I'm going to cheat since we're using little bitty numbers. And 2.2, it's 2.205 minus 2 over 0.1 minus 0. That's my slope times x minus 0, or x plus x minus 0 plus 2. There's that line. Look, that is even a little less steep, right? And that slope there, in case you want to. That slope right there is 2.05, if we were to add it there. So, if I go over here and analyze what's happening, I could even add the last one here. We got, for 0.1, we got 2.05. What does it look like our slope is trending to? It's decreasing. Do you think it's going to decrease forever? If you look at what's happening, we went down by 1/2, really 3 times there, right? But then when we started getting closer, we weren't going down by 1/2 right there. I could add in, I just did point 0.1, and I got 2.05. So it looks like probably 2 is what we're going to. So let me go back to the last slide that I was just looking at here. If I go down here and I type in the line y equals 2 times x minus 0 plus 2, that gives me this line right here. Let's see if I can make it. Let's make it thicker. And let's make it green and dotted. No. Okay. Let's make it a lot thicker. Okay. So I've made this thicker, and let's make it black. A thick black line right there. So if I look at what's happening, look at what happened as I got closer. I was here. Oh, no, let me do that. I was here at that blue line, then red, then blue again, then that green one, then the yellow. I could even do the one I did down here. Oh, that one's black. That's not going to show.
It's like one of those paintings.
A little bit.
Whenever you like move the paint can.
Yeah.
Like those.
Yeah, it is a little bit like that, or like a spirograph thing where you got those little gears and you take the pen. I don't know if you guys have ever used those. But if you click right here, there's that purple line. All of these lines get closer and closer to that black line. If we get rid of those other lines, we get rid of them. And just look, oh, don't get rid of that line, that's our graph. Just look at that point right there. That line, oh, let's go back and not make it so thick. That line right there looks like we are probably touching at one point. I don't know if I can zoom in enough for us to really see it. But it definitely doesn't look like it's crossing right there. It's just kind of bumping up against that line. So it looks like we have, found probably the tangent line at this point. Okay? So let's talk about what we just did right there a little bit. Because this was for one specific function, right? One specific function. But we would like for this to apply for any function. Okay, so first of all, we were really looking at slope for this, right? So if I have, this will come up. I know I was looking at a point, and for this particular problem, I knew I was using the point f of 0, or 0 f of 0, right? I was definitely using that point. And then the other point, that was changing. Okay, so I'm going to call it a f of a. All right, and I was finding the slope between those points. And that a was different. We did 4, we did 3.5, we did 2, we did 2.5, we did all of those different numbers there. So my slope formula was f of a minus f of 0 over x minus 0. Okay. What was I doing with my a? Oh, yes, sorry. It was a minus 0. Thank you. Oh, that's the wrong thing. Yes, a minus 0. Thank you. Oh, I keep using this, but I'm in this program. I don't need to use that. Gracious me. All right. Let's try this again. There we go. A minus 0. What was happening to that a? We used, like the first time we put a 4 there, right? And then we used a 3 and a 3, or 2.5 and 2 and 1 and 1/2. What were we doing with that number? What? We're making it smaller. Specifically, what kind of smaller? What number were we going to? 0. We were trying to get that a closer and closer and closer and closer to 0. What do we use when we're trying to get a number closer and closer and closer and closer to something? We will have an asymptote a lot of times. What do we use to analyze it? Limits, right? If we're doing this. So what we were doing is we were saying the limit as x, or well, not x because it's a. The limit as a approaches that x coordinate over here, which was 0. That's what we were doing. We were doing it theoretically or experimentally, right? We were plugging in numbers. But we were doing the limit as a approaches 0 of f of a minus f of 0 over a minus 0. Okay? So we're going to be able to extend this, and we're going to do this right now, or start doing this right now. We're going to be able to extend this so that it will work for any function. Okay? So that we can do this and find that instantaneous rate of change, that slope at that point for any function. All right? So you can put your computers away now. We are going to start on these notes. We probably won't get all the way through, but we'll get going on it today, which is fine. I anticipate we may not get through with this. We're going to work on it tomorrow as well. Already had it in the plan for that. So these are the kind of things like mathematicians were thinking about. They were like, I would like to know the slope of a curve at a single point. How could I get that to work? So they may have started off with like an equation like this. And then, there might be an extra. Then they could experimentally kind of say, oh, well, for this equation, I got this number. And then they might do it with a different equation, and they might, or at a different point. And they were looking for a pattern that they could say this will work for every function. And they found one. We're going to learn about that here in a moment. So we got to go back. We got to do a little bit of review. Okay? You can use your calculator on this one if you want. Jennifer is traveling north on I-77. She passes mile marker 9 at 5:22 p.m. She passes mile marker 73 at 6:33 p.m. What was Jennifer's average speed in miles per hour from mile marker 9 to mile marker 73? You're welcome to guess, but then I want you to figure out exactly. I don't know. I can't remember. It's not an even number. If you do that, you will get the speed in miles per minute. But if you want the answer, you would have to convert to miles per hour if you do it that way. You don't necessarily have to do it that way. Which is a simple conversion because it's just, you got to remember how to do it. Simple conversion. Because you're only converting one unit. You're just converting your minutes back to miles. Or minutes back to hours. Or you can change your minutes back to hours before 5. That should work. That might be even easier.
Thanks, calculator. Goodness.
That's it.
Luke, what'd you get, Troy?
I don't know.
You got stuff over there.
I don't even have my calculator out.
Yeah. That's because you don't have 0.9 miles per hour. You have 0.9 miles per minute.
Yeah.
So that needs to be changed to miles per hour.
Yeah, I'm not sure why we're doing
Why should you think that? I mean, what'd you get?
Unless we did it wrong.
Where was she at?
37.
77 at mile marker 9. At what time?
5:22.
Where is mile marker 9?
Charlotte.
Charlotte.
That's a good point.
At 5:22.
Why
Did she
she-
drive the speed limit at that time? Probably not. She's probably in traffic.
That should be a deep wrestling.
So she was probably at like 10 miles an hour.
Yeah. And she's probably running 75 later once she got out of the traffic, but it made her average speed much slower.
Man, it makes me think I'm laying on the get out of my way.
So she probably picked it up at around.
Just hop in the express lane. That license plate's on your parents.
We have like the
Anyway.
box.
Oh, you have it?
Put the box on the
My brother used to go to school in Charleston, and his truck was registered to my parents, so we just hopped in the express lane every time he went down.
Yeah.
Didn't bother him though.
Yeah. Yeah. So, I have seen lots of different ways that you guys are figuring this out. You should get 54.0845 there, miles per hour. So, lots of different ways work. What Troy had was he said that you went 64 miles in 71 minutes. And if you divide that, you get 0.9 something. But your answer is in miles per minute. So what do you have to do to change it to miles per hour? Multiply by 60 and you will get 54.0845 miles per hour. I saw, I don't know if I saw you guys doing this, but you could also just take that. Another thing you could do, if you got 71 minutes, if you do 71 divided by 60, that is going to give you 1.183 repeating hours. Now you just divide and you'll get this number right here. I think back here on Caitlin's, I saw this, 64 miles over 71 minutes equals x over 60 minutes. And that worked, didn't it? Got you the same number. Cross multiply and solve that, you'll get the same number. So if you're figuring out how far you can go in this many minutes, you want to know how far you can go in 60 minutes. That's a good way to do it. Did anybody else do it differently? So you did, like, you put that over 60 right there when you put it in. That'll work. Yep. That'll work. One thing to be very careful of. 5 hours and 22 minutes. If you were to change that to a decimal, what is it? It is not 522. It is not 5.22, right? Because there are not 100 minutes in an hour. So if you do change this to a decimal, you do 22 over 60, right? If you do 22 divided by 60, that's going to change that to hours. So 22 divided by 60 is 0.36 repeating. So if you were to change those to decimals, it'd be 5.36 repeating. What I see students do a lot of times when they're trying to do like hours, minutes stuff is they just change it to a decimal. But if you think about 30 minutes, that definitely helps you think about this not being the case. Because if we had like 5:30, that would not be 5.3, right? 5:30 is 5.5 hours, so it should be 5.5. So that will help you there. But that's just a basic slope formula. That finds average speed. I specifically, and some people were asking about why is she only going 54 miles per hour on 77. And I specifically did this problem for a reason. What is probably happening here is that she's leaving Charlotte around 5 o'clock and she is stuck in traffic. So she might be barely moving for a while. But then, once she gets through Charlotte traffic, she's probably back up to the speed limit, right? So, this gives us her average speed. Was she probably going 54 miles per hour much at all? Probably not. She was probably either going like 10, for a while,
80.
or 80. You know, she was probably somewhere at one of those ends most of the time, but her average speed was 54.084 miles per hour. This is average rate of speed. What we're going to be learning about is the instantaneous rate of speed. Let's practice one more average rate of speed. This is appropriate for this week. The function gives the number of students who have been voted for homecoming queen as the function of time. Time is measured in hours since 8 a.m. on the day of voting. What is the average rate of change of f of t on the interval from 0 to 4? Explain the rate of change in context of the situation. So average rate of change from 0 to 4. And we want to tell in context of the situation. We're about out of time, so has anybody got it yet? I think 13 is still low. 55.25. So,
What did you do?
okay. All right. So, we're looking just from 0 to 4, right? So, how many votes did we have during that time? Not 256. Did you use 256?
It was then counted to 35.
You have to take away the 35.
221.
So, we would do 256 minus 35 over 4 minus 0. So, you get 221 divided by 4, and that is going to give you 55.25. So, we got to explain what's happening here. This would be during the
Like the and one after you do like 256 minus 35. You do like the and like immediately.
yes.
Then it'll give you 13 points because it's based on
21 divided by 4 divided by 4. It just doubles.
so like I did that.
Oh, okay. I think that's what probably happened. You hit enter, and then it gave you the fraction, and then you hit green button enter, and it divided it by 4. If you've used that answer, you've got to go back and type it in. So during the time from 8 a.m. until noon, votes were cast at an average rate of 55.25 votes per hour. Okay, we didn't really get to finding the instantaneous rate today. We kind of looked at that investigation. We're going to look at finishing these up tomorrow, and then we'll do some practice with those. So be ready for that tomorrow.